Okay, we're going to look at 3 examples here of putting derivatives into context. So the first example we're going to look at is motion along a line. In these videos, I've already written out a lot of the problems and the examples, so feel free to stop and write down the problem. I'll give you a second here to look at all the questions related to this graph. So feel free to pause the video, but I'm going to move forward and go ahead and go over this problem. So right now we're going to be looking at a particle. It's going to be moving along the line y equals 5. And we want to pay special attention to what these examples. So SFT, that tells us about position. Okay, and V of t is going to tell us about velocity. So we're given 2 graphs that are going to tell us a lot about this, and we're going to analyze these graphs to answer these questions. So when is the particle moving forward is the first question. So the particle is going to be moving forward whenever there is a positive velocity. Okay, so because we want positive velocity, we're going to use this graph right here. Okay, so we're going to be looking at where s prime of t, which is this is the position graph, this is the derivative of position, where the s prime of t is positive. So if we look, velocity is negative, velocity is 0, velocity is positive, so that's between 3 and 4 right there, and then between 4 and 5 it's negative. So the answer to this question is between 3 and 4. Okay. When is the particle moving backwards? So that's going to be when it has a negative velocity. So that's going to be when your s prime of t is less than 0, or your velocity is less than 0. So when it's going to be less than 0, right here it's negative. So that's going to be between 0 to 2. Notice they're open circles. So, okay. And then we're also going to be negative between 4 and 5. Okay. Let's stop for a second and just double check this graph. So if we're looking at position, the slope of this line from here to here is -2. Okay. So the velocity, the slope of the line is -2. So from 0 to 2 is -2. From 2 to 3, the slope is 0, so that's why it's at 0. From 3 to 4, it's up 2 over 1, so that's why it's up at 2. And from 4 to 5, it has a slope of -1, so it's slope of -1. Okay, so that's how we got these graphs. So we could have just been given the position graph and come up with the velocity graph on our own, but they gave us both. Okay, so the next question is when is the particle standing still? So the particle is standing still whenever the velocity is 0. Okay, so we want to know when the velocity is 0, which is this part of the graph right here. So the answer to this is going to be from 2 to 3. Okay, and now it's telling us to graph the particle's speed. Well, we know that speed is the absolute value of the velocity graph. So I'm going to go up to the velocity graph, and in green I'm going to graph speed. So if I take -2 and I make that positive, it's going to go up to here. Okay. Now, absolute value of 0 is just going to stay 0. Absolute value of 2 is going to stay as 2. And absolute value here is going to go up to 1. So I'm going to graph these over the top because this part will stay the same. So what I have in green, this is speed. Okay, so this is the graph of speed. Okay, so that's example number 1. Now we're going to move on to example number 2, where we're going to look at vertical motion. Okay, so this is a different example, but still a particle is being, in this case, is being thrown upwards. Okay, so the particle is being thrown vertically upward from the surface of the moon. And as it's being thrown vertically upward, it has a velocity of 24 meters per second. So this function is important right here. This is the function that we're going to be working with. okay? And it's within t seconds. So the first thing it wants us to do is calculate the velocity. Well, we know that s of t is 24t minus 0.8t squared. So we know that velocity is going to be equal to your first derivative. So if you take the derivative, then I'm going to end up with 24 minus 1.6t, okay? And velocity is going to be in meters per second, okay? And then we know that acceleration is the first derivative of velocity or the second derivative of the position graph. So now if I take the derivative of 24 minus 1.6t, I just get minus 1.6. And we know acceleration is in meters per second squared. Okay, so the next question is, how long does it take the rock to reach its highest point? Okay, highest point is going to be when the velocity is going to be 0. So that's going to reach its highest point when the velocity is equal to 0. So that means I'm going to set 24 minus 1.6t equal to 0. So that means 24 equals 1.6t. Divide both sides by 1.6, and 24 divided by 1.6 gives me 15 seconds. Okay, so how high did the rock go at 15 seconds? So that is position. So that means I want to calculate the position graph at 15 seconds. So that's going to be 24 times 15 minus 0.8 times 15 squared, which gives me 180 meters. All right, so the next question is, how high did the rock reach it should say when did the rock reach its half maximum height? So it wants to know the time. So we know the maximum height is 180, so we want to know when it reached 90. And that's the distance graph, so it's going to be 94t minus 0.8t squared. So that's going to end up being quadratic formula here. So I'm going to end up with 0.8t squared minus 24t plus 90 equals 0. Okay, if you need me to do the quadratic formula for you, please just ask me to do it in class. But otherwise, we're going to end up with 25.6 seconds, or we're going to end up with 4.39 seconds. And 26 seconds is going to be 25 seconds is going to be too long.